This part of chapter 12 might be the shortest video I actually make for chapter 12. Just to let you know, very short video this one is. I showed you this picture in the last video where I showed you that the electron density surrounding two different atoms in a compound is distorted. Oxygen being much more electronegative, remember it's one of the electronegative hogs, here it is stealing all these electrons away from hydrogen. Well, that set this side up to have a partial negative charge. And this sign right here is the lower Greek letter delta. It's kind of like you draw an 8 but you don't finish it. And it means partial charge. Then this side, of course, would mean a partial charge of positive. So we end up with two separate poles on the molecule. So here we have di. The prefix di means two poles. So if the molecule has a dipole moment, or rather you can just say it has a dipole, all it's saying is the molecule has a separation of charge, where you have a negative on one side and a positive on the other. We would technically draw a dipole moment across the molecule, and you draw it by draw an arrow that points towards the negative end of the molecule, and on this side of it you draw a plus sign on this end of the arrow. And that's technically how we would draw a dipole moment on a molecule that has a dipole. The best part about a molecule that has a dipole is it's pretty easy to determine, especially when there's only two. If there's only two atoms, that's it, two atoms. Well, let me tell you, if the bond is a polar covalent bond, then the molecule has a dipole moment. Now mind you, that's only true, this part's only true if you're talking about two atoms. As the atoms become more large and complex, you can't always use this rule because you have to look at each polar bond and the molecule in 3 dimensions to see if it actually, the overall molecule, has a dipole moment. But when there's two atoms, good rule. If it's polar covalent, it has a dipole moment. Water has what we would call a super dipole. I mean, we're talking massive. Look at this thing. It's got a plus sign on one end of the molecule. It's got a negative over here. And we're going to talk more about what this super dipole is called later. But the reason we need to know about dipoles is see how this negative and this positive align? Look at that. We have like an electrostatic attraction. It's not quite as strong as an ionic bond, but there is definitely an attraction there, and that attraction is what gives water its crazy chemistry, break all rules sort of behavior. And if you recall way early in this chapter, I said that the shape of the molecules will allow us to make predictions about things like boiling point and surface. Oh yeah, I said surface tension and viscosity, all those things. And the shape of the water molecule gives us a dipole, a super dipole in this case. To figure out, I'll try to talk, to figure out whether or not something has a dipole, you kind of got to look at the difference between these two guys. Now remember, hydrogen sits here in terms of electronegativity, and hydrogen to chlorine, those guys aren't very close neighbors. Plus you've got the fact that hydrogen is super small and chlorine's really big. And chlorine being kind of like fluorine, a bit of a hog, not one of the big three, but a bit of a hog, this side ends up negative. And this side ends up with a partial density positive. See, all the electron density, I'll try to draw that again. All the electron density around this molecule gets sucked over to this side. So chlorine ends up with a lot more of the electron cloud than hydrogen. To indicate whether or not something has a dipole, you simply draw these two signs, or you can draw the dipole moment that looks like this, where we have the positive side here pointing towards the negative side. Why is it important? Well, when there's two atoms, figuring out a dipole is pretty easy, because if the bond is polar, then it automatically has a dipole. If it has a dipole, we can draw the dipole moment. However, as we move on, we're going to look at molecules that have more than two atoms. And if they have more than two atoms, the bond can be polar. The bond can have a dipole, but the overall molecule, well, that's what we're going to start looking at soon. We look at dipoles because we have to know about their physical properties, like boiling point, viscosity, surface tension, vapor pressure. All those things are affected by whether or not the molecule is polar and possesses a dipole. A dipole has both magnitude and direction. That's really not that important for our purposes. We just have to be able to look at a molecule in 3 dimensions and determine if it's polar or nonpolar. This is the type of molecule that we will learn to analyze. In all honesty, this molecule should be drawn with some lone pairs around the oxygen, and we'll get to learning how to do this to draw things like lone pairs and double bonds. But our goal then is to be able to look at a more complicated molecule and determine whether or not this molecule has a dipole and whether or not the molecule is polar. That's where we're headed. So let's look at each individual bond for a minute. The oxygen and carbon bond, oxygen and carbon are there, so they're not close neighbors. So this particular half, just look at this half of the molecule, is polar. That half of the molecule has a dipole. However, if we look at the other half of the molecule, it too has a dipole, which means the overall molecule is nonpolar. These two dipoles cancel each other out. So carbon dioxide is nonpolar. In order to determine whether it's nonpolar, we have to learn how to draw something like that. And that's where we're going. But the next few slides review ionic compounds, and then we're going to take a short break. And I don't know why the textbook does this, but then we're going to take a short break, and then we'll go back to learning how to draw these. They're actually kind of fun. Well, the types of bonds that you do need to know in this chapter, the first one is nonpolar covalent. And this is made by either elements that are identical or pretty stinking close to identical. They share their electron cloud pretty evenly. Then we have a polar covalent compound. And these guys don't share. And if they don't share evenly, then I can say that this bond, the bond here, this bond, has a dipole. Now, whether or not the entire molecule has a dipole moment, well, that's going to take some more chemistry knowledge. But if there's only two atoms, only two, a polar covalent, two-atomed molecule will have a dipole. Then we have ionic bonds. And ionic bonds, well, yeah, they don't even share electrons. Somebody's a thief. Who's the thief? Well, the more electronegative one. And who are the 3 biggest hogs on the periodic table? That's right, NOF. Those are the 3 big hogs. They could be paired with a cation, you have an ionic compound. They could be paired with a nonmetal, and you end up with polar covalent, as long as it's very different. Oxygen hooked with fluorine is not polar covalent. It's nonpolar because they're similar. I promised you this was going to be a super short video. Well, the next thing we're going to talk about isoelectronic series.